Hi, thanks. Good morning, everybody. Thanks for, it's very nice to have such a large audience for a talk with such a forbidding title. Hopefully I will disappoint you all by making it seem actually fairly prosaic and hopefully kind of a bit of a no-brainer that this is something we want and we should have. So my background, I guess most people know who I am. I've been working on Shapeless for years and years and years now. And also, a little bit more recently, I've been working on the type-level Scala compiler. And I've also, again, in the last year, been doing some work with Lightbend on bringing some things over from type-level Scala, or things that have at least been prototyped in type-level Scala, to the Lightbend Scala compiler. And I guess also I've been thinking about how some of these things actually will help us sort of translate things over to Dotty and move ourselves in the direction of Scala 3 over the next few years. So one of the, among the many issues that I've faced with Shapeless over the years are a bunch of problems which, until a few years ago, I guess I kind of assumed were going to be intractable. They were going to be impossible to solve in one way or another. We had issues with compile times being unacceptably long for complex uses of uses of the complex types that arise when doing generic programming in Scala. There were some really quite unpleasant issues with the lazy type constructor in Shapeless, which I kind of don't want to go into the details. It's an absolutely hideous macro under the hood. There are all sorts of very unpleasant things lurking in the background there, which again, it never seemed like there was going to be any very clear path to solving them, at least in a library. There are issues with implicit prioritization. And finally, there was the fact that although Shapeless has always been a library which trades on types and likes to use the power of Scala's type system to do the things that it does, rather than escape out of the language to do sort of metaprogramming or extra linguistic things. Nevertheless, at a few key points, it depends really essentially on a number of really quite hairy macros, obviously lazy being one example, but generic as well, which we'll come on to shortly. These are really quite hairy macros. They are very fragile. They depend on compiler internals. They are totally non-portable. There's no way that they will survive a transition to Dotty or indeed any other Scala compiler if other dialects or flavors of Scala were to come along which differed in any significant way in their internals. So this kind of prompted me, once I suppose the realization with the SI2712 fix was that actually it is really quite possible to have external contributions to the compiler and make progress on problems which had seemed to be impractical at the language level. And so since that point, I've been on a sort of journey doing various things and sort of trying to tick off some of these items. And I think it's been going quite well. I mean, the compile time issue, I think, this is stuff which is sort of prototyped in type-level Scala, but which will hopefully be landing in Lightbend Scala 2.13 very shortly, which are some, it turns out, quite surprisingly small tweaks to the way that implicits work, or at least some aspects of the way that implicits work, which dramatically speed up compile times for type-level induction. Issues with lazy have kind of gone away because they've been replaced by by biname implicits, which Martin mentioned in his talk about Dotty yesterday evening. That's a feature which has landed in Dotty. Again, is pending merging. There is a pull request against Scala for this as well. There's some work that I've done on implicit prioritization, which is up for discussion and may very well need a sip, but hopefully can move us on. The macros, the remaining macros are three general families of macros, which I think were which have been problematic. So lazy I've discussed. Witness, which is used to capture singleton types, and generic, which is used to map Scala ADTs onto a generic representation in terms of sums and products. So anyway, lazy, as I anticipated myself, has been replaced by binom implicits. Witness and the like have been replaced by literal types and value of, which they were experimented with in the type level Scala compiler for a while, and have recently landed in Scala 2.13. Generic is really the one remaining thing in Scala, in Shapeless rather, which it's still very open as to what form that should take. I've been thinking about it a long time, and for a long time, and I'm still unclear exactly what the right path forward. And I'm going to discuss some of the issues that arise in this talk. The two main things that I think are outstanding is what should Shapeless maps Shapeless generic maps an algebraic data type onto a representation type. So first question you might have is, well, what is the representation type? Do we need something special like H-lists and coproducts? Or can we get away with pairs and either or something like that? Or maybe there's a sort of a church-encoded kind of representation model which doesn't need any kind of representation type at all. And I think whereas these are things that you can be sort of somewhat kind of fast and loose about in a library, I think if you're going to think in terms of baking something into the language as a language feature, I think you need to have a fairly clear idea about which way you're going to go. The other thing, and the thing that I'm going to talk about today, is what kinds are representable, and well, what does that mean exactly? So Shapeless's generic initially only represented types of kind star. So a type of kind star is a sort of fully applied type. So it's a type with no holes in it. So something like int or string. Int and string aren't particularly interesting from the point of view of generic. They don't have a non-trivial representation. They just map to themselves, as it were. But any kind of interestingly structured type has a representation in terms of if it is of kind star, has a representation in terms of a representation type, which is also of kind star. And so the first kind of generic type class that arrived in Shapeless, it represented only those things. It kind of looks like this, more or less. This is not exactly as it is in Shapeless at the moment, but it captures the essential idea. So you can see immediately from the type parameters that the only kinds of types that can be filled in as type arguments for those type parameters are fully applied, complete types without any holes in them. And you can see them both in the type that's being represented and also in the representation type itself. Despite the fact that you know this is quite a restriction of what you might hope to be able to represent, it covers a huge amount of ground, and most of the applications of Shapeless in terms of working with I don't know a codex of one sort or one form or another, and many uses of generic programming can actually be covered by this. Nevertheless. There are some notable things which it can't do, and which really came to light as a result of trying to go a little bit further in terms of the kinds of type class instances that you can derive using Shapeless. And they mostly came up in the context of trying to derive type classes like I don't know, functor or traversable or foldable or whatever for cats, which is work that I did in a project called Kittens. Okay, so support for representing types with a single simple whole came to Shapeless later in the form of generic 1, and that can represent type constructors with a simple type argument. That's things like list or option. And again, you can see immediately in the type parameters that is the shape of the types that it will support. And also notice that the methods that map you to and from the ADT to the representation and back again, they have become polymorphic now. They're no longer monomorphic methods. Okay, and this actually gives us an awful lot of very, very interesting things. And I think we're still at the beginning of exploring exactly how far we can go in terms of deriving these more interesting type classes. But I think there is a huge amount of very, very interesting stuff that is out there for people to work with. Okay, so I can give you a very it's not a demo exactly. I'm just going to show you the sort of the rough general outline of what this this kind of stuff looks like. So we have a trait generic. We have a trait generic 1, which look more or less as shown. And then in terms of what we can do with these things, if we have a couple of simple ADTs, so we have a simple monomorphic ADT. A cat has a name, and it has a representation. So I'm not actually using shapeless here. I'm just, if you like, manually writing out the instances as you might do by hand, just for the purposes of a quick demonstration. So this is very, very simple stuff. It maps stuff from the ADT to a pair, and then back again. Then we have a simple type of kind star arrow star. And again, here you can see that because generic 1 takes type parameters with a single type argument, we're able to chase our polymorphic type, both the ADT and the representation type, through to the generic instance. And again, we have polymorphic methods here. Once we've got these things, we can do useful things with them. We can create a cat. We can map it to its representation. We can also use the typical sort of well, at least to some people, fairly familiar mechanics of doing an inductive type class derivation, say for a show instance, which is going to give you show for products given a generic, or for a functor given a generic, we can produce a functor instance for products. If you want to look at code which does this in a more robust and complete way, you will find the generic code pretty much everywhere shapeless is used. The generic 1 stuff, the project kittens is the thing to look at. But anyway, having done this, we can produce functors automatically without having to manually write instances, and then we can fmap over them and so on and so forth. Okay. Okay, so we've got support now for two kinds, types of kind star and types of kind star arrow star. Should we stop there? Is that it? Is that all that we would want to be able to support? Can we even stop there? I mean, does it make sense to give up at that point? And I think in the first instance, I think the only reason for stopping at this point would be a kind of failure of imagination. I mean, I think there's lots of very, very interesting things out beyond those two kinds that we might want to be able to do generic programming with. In terms of can we stop here, actually, I think it almost immediately falls out that we can't really. One of the reasons that that we can't is that I've somewhat glossed over some of the complications around kinds. Kinds are not just about numbers of type parameters. They're also about every time you introduce a bound on a type parameter, you generate a new kind. The existing sort of generic 1 are not going to be able to derive instances for you for types which have type parameters which have bounds. It's not even a question of going to sort of generic 2, 3, 4. You could have generic 1, but its single type parameter might not be simple. It might, instead of being a type parameter of kind star, might itself be a type parameter of kind star arrow star. Now, this might sound like it's a little bit abstruse, but actually there are some really, really nice, very simple, quite compelling examples of things that you might want to do with deriving a type class for a type with a hole in it of that shape. Now, again, this is not currently representable with Shapeless's generic 1. So kinds is about a little bit more than just number of type parameters. It's about bounds, and it's about the kinds of the type parameters themselves, and recursively so on down. And then the problem when you actually look at this is how can we support this? Using the model that I just demonstrated with generic 1, and so on and so forth, you would just end up with an endless proliferation of different shaped generic type classes, which differ only in the kinds of their arguments and the precise polymorphism of the methods mapping to and from representations. And it's something you can kind of just about live with in a library, because libraries are things which can grow in a relatively incremental and ad hoc kind of way. But I think if we're thinking about sort of adding generic or something like generic as a language feature, I don't think that's acceptable. I think a language primitive has to be something which is reasonably sort of complete and coherent and orthogonal, and it's not the kind of thing we can't, for example, I think introduce generic 1 in Scala or in Dotty, and then 6 months later decide we have to introduce another family of shapes for generics. I think we need to come up with some kind of mechanism which enables us to kind of cover all of these things. Okay, so can we abstract away the differences between the kinds? So the very first hurdle we hit, and it's incredibly frustrating in a way, is that there is literally nowhere in a Scala program that you can put types of different kinds. If you kind of want to write code which looks like we're simply applying some type constructor to some other type, and want to be able to fill the hole in the outer type constructor with types with, in the example there, either kind star or star arrow star. There's nowhere that it can be done. So what do we do about this? I mean, it seems like we've hit an impassable barrier. Well, not really. I mean, we can sort of try to encode our way around this problem. What we can do is, given we don't have any way of creating a single hole which will take all types of all kinds, but we can create, if you like, a family of holes. We can create a bunch of wrappers, each of which takes a type argument of a different kind, and then the result of applying that is going to give us a type of kind star, and we can use that uniformly. Now, obviously, we're trading off generic 1, generic 2, generic 3, ... for K0, K1, K2, K3, ... Okay, have we actually won anything? Well, in a way we have, because this is completely universal. We can use this in many contexts. Generic is one very specific type class. We might want to be able to reuse this infrastructure somewhere else. This is certainly the kind of thing that we could imagine synthesizing very simply. It's maybe not so straightforward to imagine how we would do that sort of baked into a more complex, more articulated type class like generic. Anyway, let's kind of see where this goes. So one thing it doesn't give you, okay, we can do that, but we also need to somehow or other model type application, because if you remember back a bit earlier when we were looking at the this generic 1 representation, we also notice that we actually have something that looks a bit like, well, what it is type application. We're applying the representation type constructor to the inner type. So we've got to be able to do something like type application. So let's see if we can model it, and we can try and model it via a GADT. So we're just going to capture the application of a type of kind star to no type parameters via an apply 0. We're going to capture the idea of applying a type of kind star arrow star to a single type of kind star via an apply 1, and so on. And so again, we've got this sort of parallel infrastructure of type applications. Then you can kind of make this work in terms of GADT pattern matching, sort of lurking away in the implementation of the thing, hopefully where no end users are actually going to have to see it. Okay, so this gives us a generic, which is going to end up looking like that. So this is the thing to compare with what I showed you just earlier for the generic 1. So this is something which will apply to types of kind star arrow star, and so forth. And we can imagine generalizing this and producing generics of arbitrary kinds in this way. Okay, I can show you some code for this as well. So this does actually work. So this is, where are we? Encoded. That's this one. So I'm just going to show you, so we can see how this kind of works here. So before we just had generic of cat, now we have generic of K0 of cat. And that works out the same. The functor stuff, as far as the end user is concerned, looks identical, because actually all of the gubbins relating to the kinds of the types being derived for is actually hidden away in the derivation itself. However, the derivation ends up looking quite a bit uglier. We end up with, well, maybe not. I mean, it really only affects the generic case of the induction, where we end up with a whole bunch of wrappers appearing in the context of the generic. There's some fairly nasty implementation in terms of extracting the specific operations. We're going to need to be able to actually do something with these applies, so we end up having to use GADT pattern matching to allow us to sort of move down the hierarchy of type applications to get somewhere. I guess I kind of want to skip over the details, because basically the conclusion I want to come to is that it kind of works, but it's pretty clunky. And I'm not sure I would particularly want to inflict that on anyone. Okay, so the first hurdle that we had is that there is literally nowhere in a Scala program that you can put several types of different kinds. So suppose we just drop that restriction. Suppose we just arrange for it to be possible to write a parameter in a Scala program which can be filled with type arguments of different kinds. We're not going to add any other infrastructure to the language at all. We're going to rely on being able to use type-level computation via implicits in the way that is common in Shapeless and other libraries to do anything else that you might want to do. In particular, we're not going to do any type application. We're going to stick with the type application model that I showed you the last time round. Pascal Voiteau, who's Mandubian on Twitter and GitHub and elsewhere, and I collaborated on putting together an implementation of this in type-level Scala. I forget how long ago. It's kind of over a year, I think, now. It's available in type-level Scala. We played around with it. It was a very, very interesting experiment. We end up with this. So this is, excuse me. This is rather than having a bunch of wrappers around our type arguments, now we have these bounds of any kind, which indicate that the type parameters can be filled with types of any kind. And you can see in terms of the applications further down that we're able to construct a generic type application with types of kind star and types of kind star arrow star. So it kind of looks like this is a win from a sort of syntactic point of view. It kind of seems reasonably nice. We're still encoding polykinded type application, as you can see up in the as the arguments and the result types of the to and from methods. But the sort of the mechanics there have become a little bit simpler because we can now make the type application data type itself polykinded, so we can give it a bound of any kind on its type argument. And this kind of makes things a little bit simpler. The demo, well, in terms of end user code, it's looking pretty simple. It's looking pretty similar. Now we're back to more or less where we were with the initial boilerplatey generic case. We no longer have to wrap the cat in a K0, so we can just work with that directly. In terms of the functor, well, again, that was always hidden away in the derivation. But now, if you look at the derivation where we have the generic there for the functor, again, this looks quite a bit nicer. It does and it doesn't. I mean, it saved us some work. I mean, we've traded off some wrappers for some bounds of any kind. We still have this type application problem that we have to deal with, and there are still some vaguely related type inference problems to deal with. So the conclusion that we came to was that it was a little bit better. It was still pretty clunky, and we kind of decided that actually we were going to park it, think about it a bit more, see if we could come up with something maybe a little bit more elaborate, and see if we could actually get something that was a bit more compelling than this. I mean, that offered a bit more to end users than just a little bit of syntactic cleanup. And I think we were also sort of fairly convinced that the benefits weren't sufficient to really be that compelling in terms of persuading, I don't know, Adrian, that he might actually want to merge this stuff. It just didn't feel to us as though it was sufficiently compelling and offering enough that there was too much prospect of that happening. But then, very recently, I forget how long ago, I mean, was it this year? Or if it wasn't this year, it was the end of last year, Martin announced that he was adopting it in Dotty. The initial implementation is actually very similar to the one that landed in type-level Scala, at least superficially, I mean, as far as the surface syntax is concerned. It's actually, there are some really, really interesting reasons why Martin has gone down this route. I recommend you buttonholing him and asking him about it directly. But it actually turns out that it serves the particular model that we ended up with actually fills quite a nice little space internally in the implementation of the Dotty compiler, and also with respect to some of the theory in the dot calculus. It turns out that you can, the way that you can model kinds via subtyping means that you can recover a sort of a universal top type, which I think is something that Martin had been quite keen to have, and this actually provided quite a nice, elegant way of doing it, and gets a sort of small, at least mildly interesting language feature into the bargain. As far as I don't think, as it has appeared in Dotty, it doesn't take us any further along than the last example I showed you with the version as developed in type-level Scala. But it has at least revived our interest in trying to push a little bit further and see if we can make any more headway with coming up with something which would actually make for a sort of more generally compelling language feature that actually offers more significant benefits to end users, as well as the sort of the internal and theoretical ones that clearly it has for Dotty. You know, we've been given an inch, so let's see if we can take at least a yard or two. Anyway, so the first hurdle was there's no way to put types of different kinds. The second hurdle was type application. So can we do something with that? Suppose, obviously the apply type constructor there is literally, apply of repr to I is really just meant to represent the idea that we are applying the repr type constructor to the I type arguments, whatever they turn out to be. Can we just do that directly? Why not? So the interesting thing is actually not so much what happens in the generic trait itself, but what happens in the implementations where these are things which are synthesized by the compiler. They're not typically written by hand, but we have to have some mechanism for providing, given that I'm asking for a generic of some particular type, actually producing an implementation of that type in a way which satisfies the constraints of the generic trait. So we need to come up with some kind of model which allows these definitions in the specific subtype of generic corresponding to box here to actually provide the implementation for the types in the generic trait. And what would actually almost certainly end up happening is that we end up with synthesized bridge methods somewhere or other, which we're kind of familiar with from the implementation of specialization and the implementation of trait encoding in the Scala compiler anyway. So I think something along those lines can almost certainly be made to work. This is barely even work in progress from my point of view yet, but I think it's something that I think we could. Actually, there's a typo there. That should actually just say generic rather than generic 1 because it is supposed to be extending this. But ignore that detail. So what would this do for us? So we can have a quick peek at. So this is the extended version. So in terms of what end users see, actually very little difference. In terms of what implementers of generic programming infrastructure like type class derivation see, they basically see something which is quite significantly simpler. All of the apply and type apply infrastructure just goes away. I think there are almost certainly some possibilities for simplifications of type inference issues as well, which I think are worthwhile having. So I guess there's still an open question lurking in the background about, given that actually after I think one of the earliest iterations that I've been through, there's not actually that much change in the code that a typical end user has to write. I suppose there is a question about is this is at this point it's helping library designers somewhat. It's not really helping end users very much because most of the complexity of this stuff is completely hidden from them. So I think there's definitely scope for discussion about whether or not the sort of power to weight ratio of the language feature is quite there. Current status is that there is the type level Scala prototype that I showed you earlier on. There's the initial DOTI implementation, which I think from a point of view of actually playing around with should be similar, I think, in terms of to the type level Scala implementation. From the point of view of actually aligning the two implementations, there's quite a lot of details in terms of the internals, which I think it would be very useful to backport from DOTI to Scala, and hopefully as part of the process of actually bringing that language feature to Lightbend Scala. Then I think there's lots of scope for people to experiment with polykinded application as well. And this is the kind of stuff that needs a SIP, so there needs to be some kind of fairly rigorous description of exactly what the language feature is and how it works. I kind of feel as though the range of possibilities we've got here are as yet unclear. I mean, I think it may turn out that kind polymorphism will have similar kinds of effects as the introduction of higher kinded types had, in as much as I think the very first examples we saw of higher kinded types were they look nice, but they seem to be relatively limited in scope. And I think it took quite a few years of experience with higher kinded types to realize that there are actually a very, very large range of applications for these things. I think the same thing is going to drop out of kind polymorphism as well. I think it's not quite clear exactly how far this can go, but I think there's probably just about enough immediately useful stuff that is worth pursuing. Okay, I actually have a couple of extra slides. So unusually, I've actually come in slightly under time. This is almost unheard of, which is great. I'm actually quite pleased. So some of the other immediate applications of kind polymorphism. There's a bunch of the little niggly things. I don't know if people will work with things like type tags in the macro API or compiler plugins. If you want to get hold of the type of a type constructor, so like list, the way you do it is typically you ask for a list of any or a list of something, but that of course gets you a type of kind star. It doesn't get you the type constructor. So and it's actually a fairly common bug I've seen in multiple. I have committed the bug myself, but I've seen it in other macro using libraries that people they want the internal representation of the type of list, but they end up with the type of some list applied to some type, and they forget to sort of poke out the inner type by calling type constructor on the type they get back. And the reason for that is that the type of operator and the type tag type class are parameterized with types of kind star. There's no way that you can say ask for the type of list at present because of precisely the same problem that I set up at the beginning with generic. There's no way of writing the definition of a type tag type which can accept both list of int and list as its type argument, and similarly for the type of operator. So there's a bunch of things that fall into that kind of category. There's also shapeless is typable, which is a similar kind of thing. We might want to be able to ask for typable instances, both for fully applied types and also for type constructors. Okay, I think I wanted to very briefly mention this, because I think it's actually quite an interesting example of the kinds of things I'm half expecting people will want to experiment with once the sort of sort of floodgates are open and we can play with kinds. We can be polymorphic over all kinds. How many people in the room wrestle with the problem of incrementally filling out immutable data structures sort of step by step? So, for example, as a result of filling in an interactive form or something along those lines. Or many people do that. I imagine almost everybody does that in some way or another. So there's a whole bunch of approaches that people tend to take when they do it. So one of them is they wrap everything in options. So you can, rather than having a case class representing an order which has an item name and a quantity, it has an option of a item name and an option of a quantity and so forth. So you can wrap everything in option. There are various things you could do. You could maybe have a sort of pair of twinned data types, one which has everything wrapped in option, and one which is there to represent the complete data type once you've got all the elements together. I know of some people who use shapeless records to model partial data types. One quite nice approach is to just parameterize your data type with a type constructor. So the example here is, say, we've got an order data type. It's parameterized with an f. And the idea here is that we're going to either instantiate f with option, or we're going to instantiate it with ID. ID being the identity type, which will just take string, sort of ID of string is just string. So basically the idea is that we can capture both types, both the types with optional bits and the type that's fully completed, in terms of a parameterized type parameterized over a type constructor. Then we end up, if we want something like a functor, because this order type now has it has just one type parameter, but that type parameter itself has a type parameter. So this is the example of something which is not a type of kind star arrow star, even though it only has a single type parameter. So this cannot currently be represented by shapeless's generic 1. So functor k, so this is something which is being proposed as a new type class for cats, sometimes known as h-functor in the Haskell world. Basically, it's like a functor, only instead of a map which takes a simple function, it has a map k, which takes a natural transformation. So a natural transformation, for example, excuse me, a natural transformation is something which would, for example, take an option of t onto an ID of t. Okay, and if we do that, I can just quickly show you this. We can do things like this. So if we could derive automatically a functor k instance for our order type, we'd be able to, for example, given this, so this is an option type with a default. So this is so I can actually define a natural transformation from an option-like thing to ID. So option with a default either has a given value or a default value, and a fold which is going to take basically either the given or the default value and give you that back wrapped in ID. So if I now have a functor k instance for order, then I can just map over that value to take a partial value and turn it into a completed value in ID. And I think that's kind of interesting. I think that's kind of quite a nice little thing to drop out of being able to do generic programming over types of different shapes. Okay, I'm going to leave it there. I don't know how much time there is, if any, left for questions, but if there is any, I'm happy to take questions now.
We do have time left for questions. Just give us a second to read you and hand over the microphone.
Hi. So my question is, you've shown that it works for types of kinds star to star to star, but would it also work for kinds of, well, types that take multiple type parameters? So, yes. For example, map. And
yeah, it absolutely works. In fact, we can make it work with the encoding, even without kind-polymorphism. It's clunky, but you can make it work. Okay. There's a whole bunch of the type apply stuff depends on GADTs. And as you know, there are bugs in GADTs. Right. For the example I just showed you, I had to do some slightly ugly things to make it actually work. So there's a weird thing with a nested type parameter, which is not simple, not unifying nicely with a GADT pattern match. But that's basically a GADT bug fix. So that's kind of, in principle, it works.
Okay. Cool. Thanks.
Martin mentioned yesterday there will be type lambda support in Dotty. So I wonder, because you used type lambdas in implementing the apply. Mm-hmm. So I mean, wouldn't be enough maybe to have better type lambdas?
Not really. I mean, it would help a little bit. It would get so there was some type lambda syntax in some of the files that whizzed past you. It would simplify those bits, but it doesn't solve the essential problem. Yeah, it's nice to have. I want that as soon as possible. It doesn't solve the whole problem, unfortunately. It would be nice if it did.
Thank you.
Actually, opaque types do help, in fact. So, in fact, some of those type lambdas. So there's a tuple 2k type that's used there. Actually, that really ought to be just an opaque type over a pair. And in fact, so SIP35 opaque types would actually make a bunch of that stuff go away, and that would be very nice.
Any other questions? No? Ah, one last question.
Hi. Is there any other language that support polymorphism?
Haskell is one of the, one of the many language extensions you can enable.
And do you think their solution is
well,
applicable?
things are actually slightly different for Haskell, actually. And one of the reasons is that they don't have, a big problem that we've got is that we have many, many more kinds than Haskell does, because we have bounds. Every time you introduce a bound, you produce a new kind, which means that actually even some very, very simple looking things which you would expect to be very, very basic polymorphism actually turn out to be things that you require either multiple methods with different bounds, or ideally you would want to be able to abstract over them. And this model would allow you to abstract over bounds in the same way. So I think we actually have a slightly worse problem than Haskell does, and I think this potentially works quite nicely for that.